moment. Okay, fine. We're going to talk more about 2D supersonic unstable aerodynamics today. And so we'll go through that derivation using the method which is totally different from the way it was done originally, but which is shorter. I mean, I would even claim it's a clear derivation, but that's like beauty, it's in the eye of the beholder, but it's certainly shorter. And then the good news about that is that will naturally lead us into 3D supersonic flow, which in turn will naturally lead us into 3D subsonic flow. If you watch carefully, you will see I'm not going to do 2D subsonic flow, which is actually the topic that was originally done. It was the first great advance, actually incompressible 2D flow by the great Theodorson. But his method, which is described in the book, is well worth reading in the same sense that Shakespeare is worth reading. On the other hand, well, maybe Shakespeare is actually more relevant, because Theodorson's method, which was a great intellectual advance, is a dead end in terms of using his techniques to do any other problem other than the one he did. Of course, he didn't know that at the time, right? The other thing I should share with you about Theodorson is I had the privilege of editing a book of his collected papers, and I think we still have a few copies around. So if you're interested, you have one. Have you ever looked at it? What do you think? Good. Yeah. The way I got involved in that was very interesting. There were two young women, they were young at the time, class of 1946, in the Duke School of Engineering. Muriel Theodorson Williams, who was the daughter, right? And Marie Foote. So Mrs. Williams came into my office one day 7 years ago, and I knew she was a graduate. And I just knew her as Mrs. Williams. I didn't know her middle name. And so she was very pleasant, very nice looking, attractive, bright lady. And I said, well, so delighted to have you back on campus and all that. She says, yes, well, I'm happy to be here. I haven't been here in some time. My father was an engineer, by the way. Oh, really? Yes. Yes, and he had a good career. I said, well, I'm delighted to know that. And clearly he influenced you, and we went on that. And then she said, and I've often thought I'd like to do a book about my father. I said, oh, God. I mean, daughters have this feeling about their fathers, right? And the father is, in their eyes, a giant. I thought, well, this guy probably was, an engineer for who knows, and worked diligently for 30 years. But the world is probably not really looking for a book about her father, right? And she says, yes, I don't know if you know my father at all, but his name was Theodore Theodorson. Oh, well, yes, I do know. That's a great idea. Let's do that book. So we did a book. So anyway, but when I first heard it, I truly was thinking, how am I going to get out of this? Right? But then when I knew it was Theodore Theodorson. Theodorson was really fascinating. Of course, he's best known in aeroelasticity for the 2D incompressible unsteady flow solution. He was also a fellow who had a hypothesis about turbulence. And he said that, I think they're called hairpin vortices, might be important. When he proposed that, people who looked in turbulence thought he was crazy. Now it's very fashionable. And so, that was probably 40 years ago or more, when he first started talking about this. And now, all of a sudden, everyone thinks, In fact, some people now claim that if you don't have significant vortex dynamics in the flow, if you don't observe that in an experiment, it's not turbulence, it's not real turbulence. The other thing he wrote, I don't know if I didn't include that paper in the book, but I'm not sure. He wrote a book on how you could derive a model from classical mechanics to describe all the essential elements of the experimental evidence for quantum mechanics, which was also a crazy idea at the time. But now there's some famous physicists currently who are working on that idea. So we'll see. But anyway, he was also, I later discovered, didn't tell Mrs. Williams this, He was a hard guy to live with professionally. He was something of a tough guy. And there's a book by John Anderson. I don't know, have any of you taken a course? You know, John Anderson has written several books on fluid mechanics. He wrote one on, what is it? The development of the airplane, the history of technology, or something like that. And there are several chapters. In one chapter, he talks about Theodorson and one of his disciples, Ed Garrick. I never met Theodorson, the father, but I met Ed Garrick, who was the head of Aeroelasticity for many years at NASA Langley. In fact, he was, in his generation, he was the guy. Certainly in the United States, maybe in the world. That's Garrick. And he was the disciple, and he and Theodorson wrote some seminal papers. And Garrick was a really nice guy. But according to John Anderson, in his chapter, maybe Dr. Theodorson was not the most pleasant person to live with and had very definite views on almost everything. He had a PhD in physics from Johns Hopkins. Johns Hopkins was the first university in the United States that had significant science PhD degrees offered. And so he started out in life as a physicist, but maybe reflects the fact that later on he was trying to do something in the quantum mechanics area. Anyway, we're not going to talk about his work. That's all you're going to hear about Theodorson in this course. But if you want to know what he did, it's in chapter 4. Okay, so now we're doing 2D, supersonic flow. So let me remind you what the math model is. We have this, plus this, but the y derivative we're throwing away because we're assuming that nothing changes in the y direction, right? Which is true if you have a very high aspect ratio wing, at least do a very good approximation. And then we have minus 1 over the speed of sound squared times the substantial time derivative. I'm going to use this notation, but you should understand how to take this notation and convert it to all these terms. Okay? And then we have a couple of boundary conditions, but one I'll write down, the other one I'll just allude to in a moment. This is the velocity potential, and when I differentiate with respect to z, I get the flow velocity component in the z direction. This is the fluid velocity. And at the surface of the wing, which we approximate as being in the plane when z equals 0, that must be equal to the velocity of the body, which again is this convected time derivative times w, where w, a function of x and t, is the displacement of the body. And in particular, if I had an airfoil that's very thin and is plunging through a displacement h and rotating or pitching through an angle alpha, then in particular w is minus h, where we take w positive up and h positive down because everyone else in the world does it, even though I wouldn't have done it that way myself had I been in charge back in the day when it was done, but nevertheless we're stuck with that convention. Minus the angle times x is in the flow direction, right? Minus the position wherever the elastic axis is, because that's the point where we're rotating about, right? So this is e.g., this is an example of what W is. Now I'm going to use a notation that's traditional, but may not be, again, the best thing in the world if you had a chance to do it all over again. I'm going to call this W sub A, where W sub A is all of this together. I put the A on there, stands for aerodynamic, I guess, or airfoil or something. Right? I just want to keep having to write this all the time. From an aerodynamics perspective, it's just some function that's given, right? The aerodynamicist thinks that the motion of the airfoil is given, and she's going to compute the pressure on the airfoil and give it to the structural engineer, who's a lesser mortal, so that'll be a man, right? And therefore, but then the aerodynamics is done, right? Okay, and then finally, the pressure, actually the perturbation pressure, is minus rho infinity, the free stream density, again times this time derivative, the substantial time derivative, times phi. Okay, well, I'm going to call this equation 1, this one 2, and this one 3. And this is Bernoulli's equation. And you want to call it Bernoulli's equation when you're talking to other people, because then people assume you know something about aerodynamics. If you call it something else, then people will know that you're really a bit of a faker, right? So if you call it Bernoulli's equation, they'll think you know something. Okay, now, what are we going to do? We're going to take, phi, which is a function of x, z, and t, and assume simple harmonic motion. Again, for two reasons. One is, for linear systems, we can always build up the solution for any other motion, starting from simple harmonic motion if we really want to. And also, simple harmonic motion is exactly the motion that occurs at the flutter point. So if you're only interested in computing the flutter point, this is all you need. And then again, you heard about random vibrations. Remember, if you have the transfer function, the transfer function comes from looking at sinusoidal motion. So there's an aerodynamic transfer function between W sub A and phi, for example, or W sub A and pressure, right? There's a transfer function which we effectively can compute by solving this problem. Okay, so we're going to do that. We'll call that equation 4. And then 5, we're going to take the Laplace transform of phi. We're going to define that with the symbol capital Phi. And that, by definition, is the integral from 0 to infinity of phi bar of x and z e to the minus px dx. We're taking the transform with respect to x. If you've had some Laplace transform theory before, you know usually you're doing it with respect to time, but in this case, we can do it in supersonic flow with respect to x because nothing's happening for x less than 0. So x basically behaves in a mathematical way like a time variable. It's physically a position variable, right? But it has all the same mathematical properties in supersonic flow of a time variable. By the time we do 4 and 5, we substitute that into these other equations. Equation 1 will become an ordinary difference equation in z only, right? Because time has been essentially replaced by the frequency omega, and we've taken a Laplace transform with respect to x, so now x has gone away, but the transform variable p, never to be confused with the pressure, right? Never, ever to be confused with the pressure, will appear. So if we use 4 and 5 in 1, for example, what do we get? We get p squared capital phi, because the Laplace transform of the second derivative is just p squared times the Laplace transform of the function itself. And in a moment, I'll do an aside and tell you how you can show that's true on the back of an envelope, provided it's a fairly large envelope. Right. P squared that. Then we have the second derivative of phi with respect to z. Now, I write this as an ordinary derivative because by now, the only thing that gets differentiated in this equation is with respect to z. And then we have minus 1 over a infinity squared. Derivative with respect to t generates an I omega. You see that by looking at this equation. If I differentiate phi with respect to t, I get an I omega in front of whatever. The derivative with respect to x here generates a factor p. The whole thing gets squared times capital phi equals 0. Right? So we'll call this 6. Okay. And now I'm, with malice of forethought, because I've done this before. I mean, you can do a number of things from here to get to solution, but I'm going to do it in a certain way because I have a certain goal in mind, which I'm not telling you about just yet. But you'll see why I'm doing it. I'm going to take this U outside this bracketed quantity and it's squared, right? And that'll generate a Mach number squared, right? And then I can collect all these terms so that I have an equation that looks like this. Make sure I get the sign right. I know the answer I want, so I'll do it this way. U squared phi. Minus v squared. Yeah. Now, therefore, mu squared is just everything that multiplies phi with a proper sign. So it's going to be the Mach number squared. This minus sign gets taken care of by that, times I omega over U infinity plus P quantity squared. And then there's a minus here, and this is a plus. I need another minus here, minus 1. Or minus P squared, excuse me. Okay, so this is the definition of mu squared. I'm just collecting all these coefficients that multiply capital phi, right? I'm calling it mu squared. Okay. So now I'm going to do a little sleight of hand, but I'll confess my sleight of hand later and explain how we can make this a bit more rigorous. But if I have this equation, let me write it down again so you'll see it. This is 7. What is the form of the solution for phi? He asks. This is a linear, ordinary differential equation, second order, constant coefficients in the sense that none of the coefficients depend on z. Of course, I still got omega buried in there. I've got Mach number buried in there. I've got the Laplace transform variable p buried in there. But importantly, at this stage, I'm just going to solve this ordinary differential equation, right? Once I get this phi, this is the Laplace transform, right? I'm going to invert the transform, and then I'll be done. Okay. So what's the solution? This is a good exam question too. What's the solution? What form? What? We like A? That's some constant, I don't know yet. Yeah, times what? E to the mu z. How about that? And B, E to the minus mu z. Right. Now here's the sleight of hand. I'm going to pretend like mu is a real number. And if I want to, it could be plus or minus, by the way. And so what I probably really should do is put absolute values here to be a little more rigorous. But it turns out mu can be an imaginary number too. But we're not going to deal with that yet. Sometimes it's real, sometimes it's imaginary. Now you see it, now you don't. But for the moment, to proceed onward, we're going to pretend like it's a real number. Okay, if it's a real number, and now I'm going to look at the upper half of the flow, the flow for Z positive, right? I could do a similar thing for Z negative. Z positive is above the airfoil on the top surface, if you will. Z negative is on the bottom surface. But let's look at the top surface. What can I say about these two solutions? in particular, what can I say as Z gets really large? Well, this solution seems to decay, right? This solution seems to grow without bound. So I don't like that. Get rid of it. If mu turns out to be imaginary, which it can be, then you will see that one of these solutions represents an outgoing wave, and one represents an incoming wave, and you have to throw away the one that's coming in and retain the one that's going out. That's a little more subtle. And again, it's discussed in the book, and if you're interested, I'll even talk about it in class, or you could read it in the book. But let's do this for the moment. Okay, so this is equation 9. Now, all I need to do is apply the other bound condition, which is one in the airfoil. Remember what that is? That's equation 2. Let me write that down again. It's d phi dz equals W sub A, where W sub A is all that combination, right? But I'm assuming simple harmonic motion for phi. Well, that implies I have simple harmonic motion for the airfoil, right? It's a linear system. Right. So what I'm really doing is assuming simple harmonic motion of the airfoil, which implies simple harmonic motion for phi. Okay. So I'm going to also assume that WA is some WA bar, EI omega T, right? And so when I take that in here and take the phi, because phi bar EI omega T, all the EI omega T's cancel out. You grant me that? You grant me that? Okay. But then I'm going to take the Laplace transform of this equation too with respect to x. All right? So this is now d, well, it's really an ordinary derivative now. It's d capital phi with respect to z is equal to, I'll call it capital W sub A, where capital W sub A is by definition the Laplace transform of WA bar, right? As you'll see, we never really need to compute this Laplace transform explicitly, but you may not know that. So this is now what 2 becomes, having assumed simple harmonic motion and taking a Laplace transform with respect to x. Okay, now I can use 10 and 9 to find phi, right? So I'm going to differentiate 9 with respect to, differentiate 9 with respect to z, and you get d phi dz equals minus mu, or if you prefer absolute value of mu, and b e to the minus mu z, right? Oops, sorry about that. No. But to apply this boundary condition, remember, is on z equals 0. All right, so I'm going to set z equals 0. So d phi dz at z equals 0 is just minus the absolute value of mu times b. But from the boundary condition, from above, and also using 10, this must be equal to capital W. Now using higher mathematics, B is minus capital W over mu, or absolute value of mu. Okay? So now I know, what do I know? I know phi is equal to B, which is this, exponential to the minus mu z. Now I'm going to use Bernoulli's equation to compute P, the pressure, not the Laplace transform variable, but the perturbation pressure in terms of this, which is given by this, right? And of course, I have to assume simple harmonic motion for the pressure too, and I need to take the Laplace transform with respect to x of the Bernoulli equation. Right. Or if I want to, I can just solve this equation for phi and then use Bernoulli's equation in the physical domain. I have a choice. You can do either one. In the book, in the book, we do this one. So let me, since I have that written down in the book, I can appeal to my notes. I'll do this. So here we are. And not only that, for the moment, although there is a solution known for arbitrary values at z, I'll be content to find the solution on z equals 0, right? So at z equals 0, this goes to 1, right? So phi at z equals 0 is just minus w over a over the absolute value of mu. Remember that buried in mu is the Mach number, right? Also the frequency, also the Laplace transform variable. Well, of course, this is the Laplace transform of this quantity, WA bar, right? So I can think of the right-hand side as a product of transforms. It's transform of this plus whatever this is. It's a transform of something. The way I find out what it is, I have to invert the transform, which is defined by 1 over the absolute value of mu. All right. But if I can do that, let's see, I'm going to call this 11. I'll write that down again one more time. So formally, I can write this. If you remember something about the Laplace transforms, which I hope you do, if I have a product of transforms, the inverse is a convolution integral of the inverse of the product of these two quantities, right? So phi bar, which is the inverse of this, at z equals 0, of course, is minus the integral from 0 to x, in this case, of w bar sub a. See, I didn't really have to ever compute the transform because I'm going to invert it back again. A function of some dummy variable, I'll call it c, dc, times the Laplace inverse, that's what that minus 1 means, of 1 over the absolute value of mu. And we're up. Where its argument is not c, but x minus c, right? By the way, you can make this c and this x minus c if you prefer. It doesn't matter. It's the same result. And you can show that by making a change of variable. So the real question then is, what is the inverse of this? Now, there are two ways, well, there are many ways. One way to find out is go to your library. I guess now you only need to go on the computer and type in Laplace transforms and then type in the definition of mu and look it up. Of course, that just means somebody else did the work for you before. What they did a long time ago, as it turns out, is the following. This is really equal to 1 over 2 pi I, the integral from minus I infinity to plus I infinity, of 1 over mu e to the px dp. Someone had to evaluate that integral. And that turns out to be a non-trivial calculation. But if you do that, the answer, I don't remember it in detail what it is, but I know a reliable reference where it's written down. If you do that, it turns out to be just what you would have thought it was. It's the following. It's the exponential. Oh, sorry. Back that. Let me write it a little further down so I'll have enough room. Okay. It's the exponential. Let me write this. Exponential minus I, the Mach number, omega, over the speed of sound, times m squared minus 1 square rooted times x, multiplied by the Bessel function, omega over the speed of sound, m squared minus 1 times x, and then the whole thing is divided by m squared minus 1, right? Just what you would have thought it would be. Remember, this is the easy case. This is 2D supersonic flow. Everything gets harder after this, okay? But this is the easy case. So the nice thing about it is what at least a mathematician would call an analytical solution, right? We haven't done any numbers yet. We've got analytical formulas involving an integral with this combination of functions that we insert in here, and someone tells us what the motion is, and we perform this convolution integral. Some cases you can do it analytically, other cases you'd have to do it numerically, and out pops your solution here. But okay. What else can I tell you about this? Well, a couple of things. First of all, if we set the frequency to 0, that's steady flow, right? If you remember what a Bessel function looks like, the special function goes to 1 when omega is 0, when its argument is 0. The exponential goes to 1 when omega is 0. And this thing just becomes minus 1 over this factor. That's the good news. The more sobering news is if the Mach number goes to 1, if we approach transonic conditions from the supersonic side, this term blows up. So the classical 2D steady flow theory blows up. It turns out, interestingly enough, because of the nature of this exponential and the Bessel function, you still get a finite result when omega is not 0, even though this thing is blowing up. But it's a very special limit because, you see, if you remember what this is exponential with an I. This is right. This is the imaginary I, right? So this thing is oscillating as frequency oscillates, right? And as the Mach number tends to 1, effectively the frequency becomes very high because of this factor. So this is a highly oscillatory function, and so is the Bessel function. So this thing oscillates very rapidly in frequency as the Mach number goes to 1, which is physically correct, and it does have the advantage that things remain finite, okay? If the frequency is not 0, even as you approach 1, that you get a bad answer. But you don't get an infinity, you just get a bad answer. Okay. What else? There's another limit which isn't quite as obvious in here. If the Mach number goes very high, you get piston theory, although that may not be obvious here. I'll talk more about that in a moment. If the frequency becomes very high, you also get piston theory. And that's been known more or less for a while, although I'm not sure it ever was rigorously shown until relatively recently. But the way to show that is to go back to the transform plane and take the limit as the Mach number becomes large before you do the inversion. And then it's obviously, he said, that you get piston theory. And the same thing is true if the frequency is very high. but that was only done relatively recently. In fact, I just happen to have the paper where it was done. This is some work done by some folks here in the Southeast. And at least one of the authors I know is very reliable. And the first one I'm not so sure about, but Professor Bliss does really good work. And so he checked this, and so it's okay. And it turns out you can also get the piston theory limit for large Z. And you might think, well, why do you want to know that? Well, first of all, it's fun to find it. But the other thing is that people do something called aeroacoustics, where they're interested in high-frequency oscillations of surfaces that give rise to far-field noise. For example, you might have a panel that's responding to a turbulent boundary layer, and they use potential flow theory. They use a combination of things. They do a local solution near the body. You actually use it in the Navier-Stokes equations. And then in the far field, they use potential flow theory, because if you try to use the Navier-Stokes equations in the far field, it would take forever. Well, a graduate student could do that for the PhD thesis, but if you're working for Boeing and want the answer this week, or even this month, or maybe even this year, you wouldn't want to do it that way, right? So, but you can show that piston theory gives you the potential flow solution, which is also computationally tedious for large Z. And so that's been worked out too. Okay. So what I would like, you see, you're still working on your homework, but I'm going to give you a preview of your next homework. Your next homework is to take this solution. You're not allowed to read this paper. Well, let's see if I should do it. I worked out the first two terms in an expansion in 1 over Mach number. Actually, it turns out to be 1 over Mach number squared. And also in terms of frequency. So maybe they could work out the next term of the series, right? That would be good. That would be really good. So here's what you can do. Let's go back and look at mu. Where's mu? Here we go. Recall what mu was. Mu squared, actually. Mu squared is equal to m infinity squared I omega over u infinity plus p minus p squared. Okay? And now I can write that using higher mathematics. I'm going to write that as m squared times everything I omega over u infinity plus p minus p. Now I got, if I'm going to take this m squared outside over here, I've got to put an m squared down here, right? And now I'm going to do this. This is squared too, isn't it? I think it is, yes. Fine, I dropped a factor there. Sorry about that. Square rooted, right? So here's the idea. I can simplify mu and therefore simplify the inversion. What I want to do is, well, of course, I really want 1 over mu, right? Which you can rarely write down. I want to expand this factor in terms of inverse Mach number squared. I'm going to assume that Mach number is high, and therefore 1 over Mach number squared is small. And therefore, I can treat this as a small parameter. And people still learn about the binomial expansion somewhere in your, very good. I see some shaking of heads. So you can expand this in a series of terms for large m, or small 1 over m squared. And the nice thing about it, it's m squared, right? So m is large, m squared is even larger, or if 1 over m is small, 1 over m squared is even smaller. So this series converges more nicely than you might otherwise find. So I worked out the first two terms and are given in this paper, which we will actually share with you. And so you can work out the next term. I always wanted to work out the next term, but I've been busy doing other things, and so why not assign it as a homework problem, right? If you get something interesting, we might publish it. Gee, how many authors will we have? One, two. I've always wanted to publish a paper with a lot of authors. Well, I'll wait and see how the result comes out before we decide about that. Okay, so expand solution to the next term beyond Bliss et al. And you'll see that the very first term gives you piston theory. Okay. By the way, you can also play the game where you expand in terms of large frequency, because remember, it's 1 over mu. So again, if the frequency is large, you can work things out. So you have to take a factor outside that involves frequency, and that gives you piston theory, and then you've got some other terms. It's a expansion in terms of 1 over omega, right, basically. So I won't ask you to do that unless you really want to. Okay. Now, I think that's all I'll say about 2D supersonic flow unless you press me for more. You want to know anything more? Maybe you know more than you already want to know. But anything more about 2D supersonic flow? The takeaway message is, again, it simplifies in steady flow a lot. It blows up as Mach number goes to 1. It may not go to infinity if omega is not 0, but it gives you a bad answer, as it turns out. But if omega is strictly 0, it just blows up. It just goes to infinity. And then, on the other hand, the good news is if omega or Mach number are very large, you get piston theory, which is a pretty simple theory. Okay. What else? Got enough? Okay, So moving right along, are we ready to do 3D supersonic flow? Okay. I'll write down the answer, and then in the time available. In the time available, I'll write down the answer, and then we'll derive the answer. Okay. So remember what we have here. This is 5. Phi bar at a function of x at z equals 0. And of course, it depends on omega, because we're assuming E I omega t kind of motion, is given by this integral. And I won't try to write it all down because it's a long mess. But it's the minus the Laplace inverse of 1 over mu x minus c times w bar a at c dc. Right? Now, c is the dummy variable that goes along the x-axis, right? And we're going to integrate from 0 up to some point of interest, x. Note that what this says is if I want to know what's happening at position x, nothing that happens for x less than 0 impacts the solution, and nothing which happens beyond x impacts the solution. That is, if I have a wing like this, there's nothing up here that tells me what's happening here, and conversely, there's nothing behind it. If I'm at a position x, there's nothing ahead of x equals 0 that gives me anything, and nothing behind this point that gives me anything. So it's a very limited domain of influence. Okay, that's 2D. 3D. Well, now it depends on x and y. We'll still be content for the moment, at least. go look at z equals 0. Well, you can leave a minus sign in, doesn't really matter. It's still going to be an interval from 0 to x. Yeah. Over some variable c, but we'll need another integral to take into account the span-wide variation, right? So there's got to be another dummy integral variable, eta, and we're going to have some inverse of something that depends on x minus c, y minus eta, times w bar of a, which depends on c, but of course it also depends on eta. And like this, we'll have some integral over eta. And write this a little neater, so you can almost read it. We're going to have a Laplace actually a double Laplace inverse, because we're going to have to take some transform with respect to y as well as x. That, and then we're going to have an integral over eta. This one, of course, is over c. So there are two challenges. One is to find this function, okay, and the other is to find what the limits on y are, or excuse me, limits on eta, right? Which presumably will depend on y. Actually, it depends on y and x both, as it turns out. Okay. So what I'm going to do is I'm going to tell you what this function is, and then we'll derive it. Probably not today, but maybe next time. It is the following. Again, relying on a well-known reference. It is the following. I'll call it double. It is 1 over pi, the exponential. This will be very familiar to you. X over a infinity over m squared minus 1. Right? That was the same factor we had in 2D flow. Then it all gets divided by m squared minus 1, the square root. That was also in 2D flow, right? And then we had a Bessel function, right? Well, we had a Bessel function in 2D flow, and now we're going to 3D, which is obviously a more difficult case. It must be something truly horrendous. Or maybe not. It's cosine. Cosine of, let's see, omega over a infinity m squared up m squared minus 1 to the square root. And then it's x squared over m squared minus 1 minus y squared square root. That whole thing in the bracket is the argument of the cosine function. And this is true if absolute value of y is less than x over the square root of m squared minus 1. And it's 0 otherwise. Sorry about that. Thank you. So the good news is, the Bessel function went away. The bad news is there's a discontinuity in this function, right? Sometimes it's not zero, and sometimes it is zero. It still has this singularity or bad behavior at Mach 1, right, because of this factor, and that factor appears other places too. But then, if you look at it, I think I left something out. Oh, I did. Sorry about that. I left out one other factor. I have another factor here. Sorry about that. X squared over m squared minus 1 minus y squared square rooted. Thank you. Now, it blows up if the Mach number goes to 1. It also blows up if when this thing is 0, which it is right at the edge of this boundary between when this function is the right answer and 0 is the right answer. And these lines, and you can think of this, when is this 0, right? That's a good question. Well, it's 0 when x over the square root of m squared minus 1 square rooted is equal to plus or minus y, right? And that's right, there are two possibilities. These represent two lines in xy space, right? They're linear functions of x and y. So they're two lines, and where the lines are depends on the Mach number. Therefore, they're called Mach lines. So along the Mach line, this factor goes to 0. But that's also the boundary between when this function is something and when it's 0. And that determines the integral, the limits on this integral with respect to eta, as it turns out. Right? So I'll draw you a picture. First of all, these wonderful lines are x over m squared minus 1 square rooted equals plus or minus y. These are the so-called Mach lines. And this inverse is not 0 inside the Mach lines. And it's 0 outside the Mach lines. And so if I have, I'm going to draw a delta wing, because it makes the story easier to tell. 1, 2, 3, 1, 2, 3. Here's a delta wing. And along this line, it's either the x-axis or the c-axis. Remember, c is the dummy variable with respect to x. And this is the y or the eta axis, right? Where eta is the dummy variable associated with y. And now I want to know, what do I want to know? I want to know the velocity potential and ultimately the pressure at some point. Call it xy, right? So this is some interesting point, xy. And to get the answer, I need to compute phi of xy. Sorry about that. Z equals 0 with a minus sign, integral from 0 to x. So I've got to integrate from here with respect to c. I've got to integrate from here back here. But then there's a question about how far do I have to integrate this way, right? So I'm going to leave that way for the moment. And is this function, which I won't bother to write down. I'll just write it down symbolically, 1 over mu. Well, it's not quite mu. It's a little different from mu, but closely related to mu, times W bar of C eta dC d eta. And these Mach lines determine these limits. And it turns out eta is equal to y minus x minus c over, I'll call it beta, where I'm going to define beta as m squared minus 1 square rooted. I just define it that way because I don't want to keep writing it. And this is eta equals y plus x minus c over beta. Right. Note that if c equals x, this term goes to 0, right? And the integral with respect to eta goes from y to y. That's not a very large interval. and what it amounts to is you need to integrate over this area. Now, to make these the same. So this is eta equals y minus x minus c over beta. And this is y plus eta equals y plus x minus c over beta. Okay? And now a difficulty arises. If I'm on the wing, I have that wing boundary condition, right? And so I know what's involved when I integrate over this portion of this entire region. But I don't know what's happening out here, at least not without some further thought. Okay? And so I need boundary conditions off the wing as well as boundary conditions on the wing. And what might those be? Well, if you think about it a bit, what it really amounts to is the perturbation pressure on the top, z equals 0 plus, and the perturbation on the bottom, z equals 0 minus, must be equal and opposite on the wing. But they must also be equal and opposite off the wing as well, from symmetry conditions and anti-symmetry conditions. But off the wing, the pressure cannot be discontinuous because it's just fluid, right? On the wing, the pressure can be discontinuous. In this theory, there's a pressure jump from the bottom to the top. The perturbation pressure is the same value, same magnitude on top and bottom, but they have opposite signs. It's sucking up on the top if I'm at a positive angle of attack, and it's pressing up on the bottom, right? But out here in the fluid, there's no wing to support a pressure jump, so the pressure must be continuous. It also must be anti-symmetric in that what happens plus, what happens minus must be equal and opposite. Therefore, the only way that can happen is if the pressure perturbation is 0 off the wing, which also, it turns out, from Bernoulli's equation, implies that the velocity potential must be 0 off the wing as well. So we have one boundary condition off the wing, we have a different boundary condition on the wing. So if I look at this equation, on the wing, I know this, but I don't know this. Off the wing, I know this, namely it's 0, but I don't know what the effective fluid velocity is, because remember this is really the fluid velocity, which I'm setting equal to the body velocity when I'm on the wing, but when I'm off the wing, I can't do that. So what I need to determine is I effectively need to determine this off the wing and this on the wing. Right? But it's okay. I've got an equal number of knowns and unknowns. I'm in good shape. And so what I basically would do is I would write a computer code. Probably not ask you to do this. They're commercially available. Write a computer code. I divide this area up into boxes, right? And in each box, I assume either this or this is a constant. Actually, off the wing, I assume it's only constant at 0. And then I set up a matrix equation, right? And I rearrange things so all the knowns are on one side and all the unknowns are on the other side, and I do a matrix inversion, and I'm done. Okay. And normally, for numerical reasons, you make sure that the boxes are such that the diagonal of the box is along the Mach line. It turns out that gives you a better numerical behavior than other possible choices. You don't have to do that, but that gives you better numerical behavior. So the methods that people have employed historically for supersonic flow are called Mach box methods, because the boxes are always aligned such that the diagonal is parallel to one or the other of the Mach line. Okay, so I guess the other thing I need to do is derive this function, or show you how to derive it. And yeah, we got 10 minutes. That's enough time, don't you think? Okay, so let's do that. What are we going to do? We're going to do the same thing we did before. We still got our equation like this. All we're going to do is add another term, like so. And remember what we're going to do? We're going to take phi and say to the phi bar ei omega t. We're still going to take a Laplace transform of phi bar and call that capital Phi. And if we do that, that will reduce this partial difference equation down to a partial difference equation in z and y only, right? But I don't know how to solve partial difference equations except numerically or by reducing a partial difference equation to an ordinary difference equation, which I can solve analytically. So I've got to do something about this term. I got rid of this term basically by transforming with respect to x. Well, maybe I should transform with respect to y. Why not? But I cannot take a Laplace transform with respect to y. Why not? Because things are happening for y less than 0 as well as y greater than 0, right? So the only other transform I know is Fourier. So I will take a Fourier transform with respect to y. Yes?
Can you assume symmetry?
Say again?
Can you assume symmetry on y 0?
There might be, but then there might not be. It depends on what your wing looks like. But it doesn't solve the problem. Are you thinking if I invoke symmetry, I could use the Laplace transform?
Yeah.
No, unfortunately not, because it's physics. The parts of the wing and the flow for y greater than 0 are interacting with the parts that are less than 0 and vice versa. So, yeah, unfortunately not. Sorry about that. I mean, when you do the numerics, you might be able to. That is, when you get down to that equation, that integral equation, you might be able to invoke symmetry then, right? So you might only need half as many boxes if you invoke symmetry and add symmetry. But you can't use Laplace transform. That's a step too far. So what's a Fourier transform look like? Well, it's just well, I'll call it phi star. I think that's what I call it. Fourier transform of this, define that as phi star is equal to phi e to the minus I gamma y dy integrated from minus infinity to plus infinity. Right? Oops, sorry about that. Right. And so what that does, yes, go ahead.
Are we transforming capital P over this?
Well, we're doing this. That gives us the phi bar. We're taking the Laplace transform phi bar. That gets us to capital phi. Now we're taking a Fourier transform of this, and I'm going to call that phi star, and that's by definition this. And what that does is, remember what we ended up with before? In 2D, we ended up with b squared minus mu squared phi equals 0. What we're going to end up in 3D is we're going to end up with b squared phi, it's a star now, right? Minus mu squared plus gamma squared, where gamma is the Fourier transform variable with respect to y, phi star. So, in transform space, it's just as easy to solve it as it was in 2D form. This is not the way it was done originally. I will not distress you by pointing out how it was done originally. But using transform methods, you do the same sort of thing. And then just all you need to do is you need to do a double inverse of this quantity, right? Or 1 over this quantity, 1 over the square root of this quantity. And that's what gives you that function involved in the exponential and the cosine, and shows that you have a discontinuity along the Mach lines and all those other things. So this is not too bad, right? In terms of deriving the governing equation, but now you need to do some numerics beyond just a simple quadrature. You actually need to formulate a set of matrix equations and do some numerical calculation with boxes on the wing and boxes off the wing. You keep track of what you know on the wing and what you don't know, and what you know off the wing and what you don't know. And do all the rest of it. But this has been done. When I was about your age, this was a new method, and we were using it at the Boeing company, and it was gangbusters. But now it's just a piece of software that Zona, and I'm not sure who else would be happy to sell it to you. In fact, there's an alternative way. We're going to do subsonic flow, and you can also, and we'll use a different method in subsonic flow, somewhat different method, although formally similar. In subsonic flow, we cannot take the Laplace transform with respect to x, right? Because things are happening for x less than 0, because we're not moving fast enough to keep ahead of the speed of sound. We're moving at less than the speed of sound, so the flow is being disturbed before we get there, right? So we're going to need to take a Fourier transform with respect to both x and y. But it will formally lead to the same kind of a solution in transform space. But then when you do the inversion, because the Mach number is less than 1, the inverted integral has a different and much more complex form for subsonic flow. Okay. We've reached 11:20. This is a good stopping point. Questions? Further questions? You're all reading chapter 4, checking all those equations, make sure we got them right. Good. I think we eliminated most of the typos in the last edition. There may still be 1 or 2 floating around. So if you find one, there's extra credit for finding a typo. All right, good.